What if our future home wasn't in our solar system at all, but orbiting a distant star light years away?
Could an exoplanet actually become humanity's next Earth?
Imagine stepping outside and looking up at a sky that is not Earth's sky. Imagine a sun that looks redder and a pair of unfamiliar constellations. For centuries, humanity has dreamed about other worlds. But with modern telescopes, we've moved from dreams to data. Thousands of exoplanets discovered, many in the so-called habitable zone. The big question now is practical.
Could any of these worlds become our future home?
In this video, we'll examine the science, the engineering, and the ethics behind leaving Earth for an exoplane, and whether it's even realistic in the next few centuries. First, a definition. Astronomers talk about the habitable zone, the orbital region where a planet could have liquid water on its surface. But habitability is more than just distance from a star. It depends on atmosphere, magnetic field, planetary mass, geological activity, and even the star's behavior. A planet in the habitable zone around a volatile red dwarf might get blasted by flares. A planet in the habitable zone of a stable sun-like star might still be lifeless if it lacks an atmosphere. So, the first step in evaluating any exoplanet is a long checklist: size and mass, density, orbital eccentricity, atmosphere composition, greenhouse effects, presence of water, and stellar activity. Let's consider some real candidates scientists keep an eye on. Proxima Centauri b is only 4.2 light-years away and orbits the nearest star. It sits in the habitable zone, but Proxima is a flare star. Its eruptions might strip any atmosphere. The TRAPPIST-1 system has multiple Earth-sized worlds, some in the habitable zone, but that star is ultra-cool and tidal lock-in or intense radiation may be issues. Kepler 186f was the first Earth-sized candidate in a habitable zone, but it's far away, and we don't know its atmosphere. LHS 1140b and Gliese 667cc are other examples. Each candidate brings hope and frustrating unknowns. Our instruments measure size, mass sometimes, and often hints at atmospheres via transit spectroscopy. But the details needed to say this is livable are still elusive. Even if we find the perfect planet, distance is the wall. The nearest stars are light-years away. Proxima Centauri is 4.2 light-years. With today's rockets, it would take tens of thousands of years. So people propose advanced propulsion ideas: fusion drives, antimatter engines, beamed sails like breakthrough starshot, and hypothetical warp drive concepts. Each comes with immense technical hurdles: energy requirements, radiation shielding, system reliability over centuries, and the psychological and sociological challenge of multi-generation crews. Another approach is slow colonization, seed ships carrying spores, robotic terraforming, AI caretakers preparing a world before humans arrive. But this raises time frames of centuries to millennia. If an exoplanet is marginal, for example, thin atmosphere or hostile climate, could we terraform it? Terraforming at stellar distances scales the problem by orders of magnitude. You'd need to change atmospheric composition, introduce greenhouse gases, perhaps alter axial tilt, and seed biospheres. For a planet much larger or with different chemistry, terraforming could be impossible. A more practical strategy may be adaptation: domed habitats, underground cities, genetic adaptation of crops and humans, and artificial biospheres. The moral question is, do we have the right to radically transform an alien world? If life already exists there, terraforming would be ethically problematic. Next, this is not only an engineering project, it's a civilization decision. Who decides who goes? How are resources allocated? Do we send the wealthy first? Do we send experimental seeders who will never return? And if we find microbial life on an exoplanet, do we colonize it? International law, planetary protection protocols, and planetary ethics would need to evolve. Moreover, leaving Earth would not solve problems like inequality or climate change unless space expansion is coupled with a profound change in human priorities.
So, could an exoplanet be our future Earth?
The scientific answer is maybe, extremely far in the future, if we solve astounding technical and ethical problems. We are learning to identify promising worlds, and our instruments will improve. Yet the reality is sobering. Travel times, planetary environments, and the enormous energy and social coordination needed make exoplanet colonization a multi-century, if not multi-millennial project. That said, exploring and preparing, sending robotic scouts and improving spacefaring tech is a wise investment. If humanity endures, exoplanets might eventually be part of our story. For now, the immediate question remains, can we make our one habitable planet Earth sustainable for the long haul? Our future on other worlds may depend on how we treat this one.